5G has come. Millimeter wave becomes the key technology for ultra-high data rate services. Consider we have a 5G wave base station and center server, serving a 5G user. Under normal condition, we will have line-of-sight wave transmission to the user. The wave base station performs beamforming, achieving ultra-high data rate to gigabit per second level. However, if we have blockages, the wave signals will be severely blocked. Non-line-of-sight transmission may also take place with weak signals. All these problems lead to disconnection and low service quality to the 5G users. Therefore, Reconfigurable Intelligent Surface, or we call RIS, is employed as a powerful solution. Different configured RIS can help improve the system performance. The beam signal firstly transmits from base station to RIS. Then, RIS instantaneously reflects the desired signal to the user without either blockage or non-line-of-sight losses. By appropriately deploying RIS, we can improve wave link quality without any losses. Then, the problem is, where and how should we deploy RIS for high performance? Here comes the solution: i-Dris. Proposed i-Dris system has dealt with the deployment issues, such as fiber cost, additional control signal, laborious measurement, and out-of-date dataset. i-Dris, short for Intelligent Rapid Deployment for Reconfigurable Intelligent Surface, has substantial benefits. No fiber links and control signals are required. Capable of automatically deploying and measuring. Auto-learn from history without re-measurement. No offline training required. Also, it's quite robust to different environments, with attainable high data rate improvement. In the following, we are elaborating i-Dris highlights. From system perspective, we demo the integration prototype of communication system of Nokia 5G base station and wave RIS. For the commercial wave base station, it can support scalable transmit power under MIMO with 32 wave beams. The peak data rate is up to 1 gigabit per second. In our system, we deploy RIS to improve signal quality, which is previously suffering from blockages and non-line-of-sight paths. The RIS, or so-called electromagnetic surface, ES, is manufactured with predefined beam radiation pattern and phase shifts on each metamaterial-based elements. As a result, we can have RIS with different numbers of elements and reflection angles. As for RIS deployment, we equip RIS on an auto-guided vehicle, AGV, for labor-free deployment. After everything is set up, wave base station will initiate downlink transmission. We will have an edge monitor to observe rate performance from the wave receiver end. The GUI interface will show the packet delivery information and instantaneous downlink throughput under different channel conditions. Afterwards, instantaneous throughput is transferred to AGV. AI algorithm i-Dris will be performed on AGV. And, finally, the deployment location will be determined. From algorithm perspective, i-Dris is designed with multi-time scaled temporal reinforcement learning for AGV RIS deployment. The key concept of newly designed learning is based on weighted previous observations, current reward, and probabilistic action selection. Here, we provide a toy example. Initially, we have small number of random actions to collect some initial data for RIS deployment. The agency with actions will interact with 5G base station, deployed RIS, and user equipment. We can then acquire reward values as wave RIS throughput performance. All data is stored in AGV memory, with current observation and historical deployment outcomes. Afterwards, AGV performs multi-time scaled temporal reinforcement learning by initially deciding different time scales for historical information. It then clusters data with the same action in each time scale to obtain per group statistics, which represents as the weights of future actions. Furthermore, current observation is significantly weighted because of its high correlation to future action and environment. The optimal AGV action for RIS deployment is finally selected with its maximum value. Its selection includes either move to another position or remain unchanged deployment. In the followings, the experimental scenario is shown, with total area 30 by 15 meter squares and deployment area 15 by 8 meter squares. The prototype equipment of i-Dris system includes Nokia 5G wave base station, the receiver of customer premises equipment, CPE, and the AGV RIS. Several reference receiver points are tested, such as non-line-of-sight transmission, which contains out-of-operation range of RIS and in-range RIS. Some other points are for blockage cases, having slightly blocked by stairs, or the second-order wave reflection path. This is the heat map result of exhaustive measurement in terms of deployment throughput at the receiver point 5. Notice that it takes around 1 hour to collect more than 100 test points. For our i-Dris system, AGV equipped with RIS converges with increasing throughput. Under harsh start point in test case 3, AGV requires much more learning steps to achieve better performance. Compared to exhaustive baseline, considerably lower deployment time of i-Dris is accomplished. Moreover, quantitative results of i-Dris are evaluated. First of all, different severe environment effects are considered. The optimal line of sight throughput is measured offline, with around 900 megabit per second. We can see that throughput degrades due to non-line of sight and blockages. Also, lower rate is observed with higher reflection orders. Compared to the case without RIS deployment, we have twice rate with about 800 megabit per second. Here, different RIS's configurations are conducted. Similarly, lower rate is induced by blockages, as well as non-line of sight paths. Under such circumstances, i-Dris has 200 to 400 megabit per second enhancement with the aid of RIS. Third, we can know from results that higher rate is achieved when an operating beam width range of RIS with 900 megabit per second rate. Furthermore, different human behaviors, such as human blockages and holding phone, are evaluated with respective 650 and 900 megabit per second rate performances. At last, different communication distances are experimented under different wave signal reflection orders. i-Dris with single RIS can attain 800 megabit per second throughput. On the other hand, i-Dris with multi-RIS enhances with maximum 90% more rate compared to no RIS, false deployment, and single RIS case. Here, we have listed existing state-of-the-arts of RIS. We have compared our proposed i-Dris system prototype to existing systems and schemes in academia and industry. Our i-Dris is a system-level prototype. Most of overhead or additional costs are not required, such as RIS configuration, fiber link, control signal, laborious remeasurement, channel estimation, and offline training. Additionally, performance is largely improved, with maximum 980 megabit per second throughput, more than 30 dB SNR gain, 3.6 times improved rate, deployment time less than 10 minutes, and also high robustness to the environments. These are all our benefits of i-Dris. i-Dris keeps exploiting 5G path to next generations, making future life better.